I mentioned that this chapter 6 is your second last chapter for this semester, and so far we had been dealing with the open system, closed system, energies associated with those systems, and primarily the point of discussion or the analysis was based on the first law. We had looked into different properties associated with first law. We looked into the internal energy and enthalpy, the two parts of energies, the flow work, all associated with the first law. There was no mention of the second law of thermodynamics. This chapter would basically lead you towards the need, understanding the need of second law of thermodynamics and the basics that you will learn why is there a need of second law specifically, what are the statements associated with the second law of thermodynamics, and a specific property which we have not touched so far is entropy. So we'll be looking into entropy on the basis of what we'll cover in chapter 6, although the property specifically would be introduced in chapter 7, but the foundation for that property or the background for that property, the need for that property would be established in this chapter. So this is about the sixth chapter on second law of thermodynamics. Let us have an overview of what specifically we would cover in this chapter, the topics that will be discussed in this chapter. So we'll start with the introduction to the second law. And while we are moving towards the introduction to the second law, we need to have an understanding of why is there a need for the second law, what is the inadequacy of the first law that requires some other law to be there, which happens to be the second law. And once we understand that, we'll develop the concept of the concept of quality associated with it, the fact that energy is not merely judged by the conservation of energy or quantity, but there's a concept of quality associated with it, and the facilitation provided by the second law. There is more than one aspects which are related to second law. It's not just that there is only one phenomena that we can extract out of second law. There are multiple features that the second law help us identify. So what are those features? We'll look into that. Then we'll move into the concept of thermal energy reservoirs. What are these reservoirs? Why do we need them? How do these reservoirs are recognized? And for what purpose these reservoirs are being used? Once we have the understanding of thermal energy reservoirs, we'll be basically moving towards heat engines. Heat engines is a very important aspect of energy transformation. There will be some basic questions that are basically addressed by heat engines. So we'll define heat engines, the characteristics of heat engines, on what method these heat engines operate. We'll look into the fact that the heat engines, do they necessarily have to be followed by fluid having thermodynamic properties, or is it that any mechanical cycle could operate to result in the formation of heat engine? And once we know what a heat engine is and what its characteristics are, we'll define the thermal efficiency of the heat engines, how good or how bad an engine is. An essential part of heat engine would be the heat which is being released out of the engine in order to have a continuous operation of the engine. So why is it necessary that we cannot have an engine without releasing that amount of heat? This is a necessary question that would be addressed within the same domain. Then you will, once you understand the thermal efficiency and the need of heat dissipation process in order to operate a heat engine, you will move towards the statement that defines second law. It is a statement which basically is a fundamental statement of second law. There are multiple statements of second law, but and this is one of the statements which necessarily directs the direction of a process or whether the process could take place or not. So we'll look into the Kelvin Planck statement. The second category of components that we'll be looking into would be refrigerators and heat pumps. They operate exactly in the opposite manner as that of the heat engines. Their purpose is exactly the opposite. And in refrigerators and heat pumps, we'll be focusing on the coefficient of performance, the measure of how efficient your refrigerator or a heat pump is essentially coefficient of performance. In case of heat engines, thermal efficiency basically defines how good or how bad your heat engine is performing. But in case of refrigerators and heat pumps, it is the coefficient of performance COP which defines how good or how efficient your refrigerator and a heat pump is. Again, we'll begin with refrigerators. We'll cover heat pumps also, and based on the principles that will establish for refrigerators and heat pumps, we will develop another statement, or we'll understand another statement, which again is a statement for the second law of thermodynamics, and this is known as Clausius statement. This again relates to the operation of refrigerators and heat pumps. Moving on, we'll also cover the understanding for reversible and irreversible processes. Reversible processes, I give you a brief idea, they are ideal processes. They represent the ideal nature of a process, although that process cannot take place, any process cannot take place in an ideal manner. There are certain irreversibilities. There are certain irreversibilities associated with an ideal process, and these irreversibilities basically result in an irreversible process. So ideal process provides basically the benchmark for us that what is the maximum we can achieve out of a process, or out of a, if let's say we are talking about a heat engine, reversible process, if heat engine is operating on reversible processes, that means it is giving you the maximum efficiency. So to gauge what is the maximum you can extract out of a heat engine, you will have to study the system under reversible processes. And how much the process deviates from the ideal process is basically governed by the irreversibilities associated with those process. So we'll see what these irreversibilities are, and then we'll classify the irreversibilities as internally and externally reversible processes. Internally reversible internally reversible processes are processes in which the system would come back to its original state after completing a process and coming back to its original. I mean, if you perform a certain process on a system and the system is able to get back to its initial condition internally. There is no irreversibilities present within the system, then it's an internally reversible process. If there are no irreversibilities present in the system and the surroundings as well, that's an externally reversible process. But we'll look into them in detail. Then comes the Carnot cycle. Carnot cycle is basically based on a reversible process. That's an ideal cycle. It is the ideal cycle that you can have for a heat engine, and this cycle basically defines the maximum theoretical limit of efficiency that you can extract out of a working cycle or cyclic process. And based on that, you will define the Carnot principles. There are certain principles associated with those with the Carnot cycle. So we'll look into them also. Thermodynamic temperature scale, although we have mentioned about it uh, uh, very lightly in the first few chapters where we looked into the temperature scales, but we'll look into them in detail in this chapter. Then once we have defined the Carnot cycle and the principles, based on those principles, we will uh, basically study the Carnot heat engine. Before that, the heat engine we'll study would not be a Carnot heat engine, but we'll study the heat engine in the light of Carnot principles, and will determine the maximum efficiency that a heat engine could have Based on that, we'll define the quality of energy, again, the concept associated with the second law. And we'll also, based on the Carnot principles, we'll also study the Carnot refrigerator and heat pump. That is, again, the behaving, uh, ideally behaving processes for a refrigerator and heat pumps. So these are some of the concepts that we'll be introducing in this sixth chapter. Let us move with the uh, first part, which is introduction to the second law. So far, what we have studied is that the first law defines the conservation of energy principle. That means energy could neither be created nor be destroyed. It can only change its form from one form to another. And this law is equally applicable to closed systems and open systems. And so far, whatever analysis we have done, it is based on the first law, energy balance equation that we have developed. It is based on the first law. And as it is mentioned, it's a conserved property energy, and there is no process which has or which is known to have taken place in the violation of the first law of thermodynamics. That means first law of thermodynamics, if that is not satisfied, no process can take place. You cannot say E in minus E out, or E in is not equal to E out for a steady state process. That's not possible. But uh, again, as it says, that a process must satisfy the first law to occur. But the issue is satisfying the first law alone. Does it mean that the process would actually take place or not? If that question is being placed in front of you, can you say that if a process is being satisfied by the first law, the process would take place or it would not take place? Can you comment on that?
सर होना तो चाहिए.
So I've got who's this, by the way? Mateen?
Yes, sir.
All right. So Mateen says that if the first law is satisfied, process should take place.
No, sir.
सर एग्जैक्टली कह
No,
नहीं
sir.
सकते हैं सर कि
All right.
होगा
Just
सर
give
कि
me,
हर प्रोसेस होगा.
hold on for a minute. Just give me one person at a time. One person at a time. Yes.
सर एग्जैक्टली एवरी प्रोसेस विल नॉट अकर.
Sorry.
सर
No, sir.
एवरी
Sir,
प्रोसेस हम नहीं कह सकते कि अकर होगा.
Arshad, if I'm able to hear you clearly, you are saying that uh, whether the
सर आई एम
process
सेइंग
would take.
दैट on due to only first law not every process can occur.
All right.
sir,
So Arshad,
sir.
just a minute. Arshad is saying that it is not necessary that every process would take place if the first law is being satisfied. This is another view. Yes. What is the third view?
सर कोई प्रोसेस अगर नहीं करेगा अगर सिर्फ फर्स्ट लॉ सेटिस्फाई कर रहा है तो कोई प्रोसेस
So
सिर्फ फर्स्ट लॉ.
okay. So who's this?
Ali Asif, sir.
Sorry,
Ali Asif, sir.
Ali
Ali
Asif.
Asif.
Ali is saying that no process could take place if the first law is if the first law alone is satisfied. Clear? This is Ali what you're saying.
सर केसेस पे डिफर करेगा.
Sir, maybe or maybe not.
So there's multiple answers. One answer that I have got is that first law is satisfied. If first law is satisfied, the process should take place. That is the answer given by Mateen. Ali says that no, it will not take place if the first law is satisfied alone. And there are other opinions that it may take place, it may not take place. All right, these are the opinions.
Yes, sir.
Not the conservation of
Yes.
energy, but it cannot
I'm just asking whether it would take place or not. Don't give me any explanation for that.
no, sir. Sir, लाजमी नहीं है सर कि बस
That
के
I mean, all right. So the opinion has been covered. The opinion has been covered that one opinion is that first law satisfies. If the first law is satisfied, the process should take place. The second opinion is that it may or may not take place, and the third opinion is that no, it will not take place. All right. These are the three opinions. Yes.
जी सर.
All right. So let's say and look at this example to understand whether the first law, if it is satisfied, the process would take place or not. So you have again, we have seen this example so many times. You have a hot cup of coffee, and it is being placed in a cooler room, cold environment. So a hot cup of coffee is placed in a cooler room, and it eventually cools off. That means there is, let's say, heat is transferred is 15 kilojoules. 15 kilojoules of heat is being transferred from the hot coffee to the surroundings. This is the result of placing a hot cup of coffee in a colder room. So the amount, first law says the amount of energy lost by the coffee is equal to the amount gained by the surrounding air. So the coffee lost 15 kilojoules and the surrounding gained the same 15 kilojoules. The first law is satisfied. And if we say, is it possible that the hot coffee gets even more hotter in a cooler room as a result of heat transfer from the room air? That means if the room has extra 15 kilojoules of energy, which is at a colder temperature, is it possible that the 15 kilojoules from the room it is extracted and the hot cup of coffee gains 15 kilojoules of energy and the temperature goes up? Is it possible?
No,
No
sir.
sir.
No, sir. No, sir.
In other words, the first law is still satisfied. 15 kilojoules taken from the room, 15 kilojoules consumed by the cup of coffee. But if the first law is satisfied, the amount of energy lost by the air is equal to the amount of energy gained by the coffee. The first law is satisfied. In such a case, what do you say? Would the process take place? The first law is
No, sir.
satisfied.
No, sir, it wouldn't take place.
वो सर बराबर है, कोई सिंक ही नहीं होगा.
Forget about that. You say first law doesn't talk about any sink, any temperature difference. It simply says that energy is conserved. Energy can transform from one form to another, but it cannot be created or it cannot be destroyed. In this case, if you see, there is 15 kilojoules of energy in the room, and the same 15 kilojoules of energy is gained by the hot cup of coffee. So the first law, it doesn't get violated.
No sir, it doesn't.
So, so should the process take place?
According to first law, yes
No,
sir.
sir.
All right. So now I have an opinion that according to first law, this process can actually take place. Let's have a look at some other example. We have weight attached to a shaft, and the shaft is basically placed within the room. And as the weight moves downwards, as the weight is attached to a rope which is mounted upon the shaft. So as the weight moves downwards, the shaft starts to rotate. As the shaft starts to rotate, the internal energy of the system goes up. As the internal energy of the system goes up, the temperature goes up. So that means there is heat being transformed to the system as the shaft rotates or as the weight goes down. So basically, weight going downward results in the heat being generated in the room. Is this clear? Is the point clear?
Yes sir.
Yes, sir.
जी clear है?
Yes sir.
Yes, sir.
All right. Let's look at it in another way. Now, if I provide the same amount of heat, initially work converted into heat. If I provide the same amount of heat to the shaft, would the shaft start rotating? So the same amount of heat, would it rotate the shaft so that this weight start moving upwards?
सर पॉसिबल
No
है
sir.
जी,
सर पॉसिबल है
that
No
means
sir.
No, sir.
you are talking about the knowledge of first law. Based on the first law, if the heat is being provided the same amount, you know that work provided resulted in the generation of heat. If the same heat is provided back to the shaft, would there be any work generated based on the first law?
यस सर
So, based on the first law, your answer is yes. But out of your intuition or out of your understanding, whatever you understand of thermodynamics, do you think this would happen?
No,
No,
sir.
sir.
All right. So in actual, you believe that this would not happen, but the first law says that this process can take place because energy is conserved. Whatever amount of work resulted in the generation of heat, if the same heat is provided to the shaft, this should start rotating. F- First law doesn't get violated in this case. In another example, you have a wire which is connected to a battery. So this battery is generating electrical work. As a result of this electrical work, there would be heat generated in the system due to the resistance caused by the wire. So heat would be generated as a result of electrical work. Electrical work would result in the generation of the heat. Now, if I turn off the power source and I supply some heat to the wires, would that heat result in the generation of electrical work
So
based on the
based on
first law?
first law, yes.
No, sir.
Yes, sir. Based on first law, yes, sir.
So based on the first law, the answer is yes. But based on your intuition or your understanding, what is the answer?
No, sir.
No. So your intuition says that this is not possible, but the first law says yes, it is possible because the energy is conserved. So there is certain information that needs to be checked. It means that you are saying that process could occur spontaneously in a certain direction and not in the reverse direction. That means work was converted to heat. It was whether the shaft work or whether the electrical work, it was converted to heat. But based on your intuition, you say that heat, or based on your observation, you say that heat cannot directly convert into work, whether it's shaft work or electrical work. So there is one-way traffic that is going on, or there is a single direction in which the processes are taking place. This is what you have observed. Although still the first law doesn't negate that. First law doesn't negate the reverse direction. But based on your observation, you say that there's only a single direction in which the processes are taking place spontaneously, without any effort. So it says that the first law, it places no restriction on the direction of a process. That means satisfying the first law, it does not ensure, it does not ensure that the process can actually occur. It further means that whether your first law is satisfied or not, it is no guarantee that your process would or would not take place. You need to have some additional information in order to decide whether your process would actually take place or not take place. This is basically uh, the inadequacy of the first law, which is being addressed by the second law. So the need for the second law is to have an understanding that whether a process would take place or not take place. First law is satisfied, but it doesn't tell me, or it doesn't give me any guarantee that the process would take place. So I need to have certain uh, authenticity or certain mechanism to decide whether the process would take place or not take place. This is where the second law comes to play its role. That means if this is the process which is flowing through the circuit, if your circuit breaker is off, first law is not satisfied, the process would not take place. But even it is satisfied, you need to have an understanding whether the second law is satisfied or not to decide whether the process would actually take place or it won't take place. So far, is it clear?
Yes, sir.
Yes,
All
yes.
right. All right. So now the information that we get out of first law or second law, what is the information that we can extract out of second law? As it says, the process must satisfy the first and the second laws of thermodynamics in order to proceed. What is the information that we can extract out of the uh, second law? Any guess? What information can we extract out of the second law?
Sir, the path of the process, I mean, किस direction में process होगा?
Very good. So the first thing is that it gives you, or it identifies the direction of the processes. in which direction would the process takes place spontaneously.
Possibility,
G?
possibility of a process. Or a
Possibility of
process.
a process, direction of a process, yes. This is the first thing, but this is not the only thing that is being uh, extracted out of the second law. The second thing is that it gives you information about the quality of energy. The first law essentially deals with the quantity. The second law basically gives you information about the quality. The first law is concerned with the quantity of energy and the transformation of energy from one form to another, and there is no regard to the quality. However, the second law provides necessary means to determine the quality as well as the degree of degradation of energy during a process. That means if certain process takes place, your system moves from state 1 to state 2. This would give you a tool to analyze how much of your quality has degraded as your system moved from state 1 to state 2. Or, in other words, what is the quality of my energy at state 2? And because a process could move from one state to another state in various ways. So, what is that mechanism that would give me the maximum quality at state 2 also? This is the second aspect associated with the second law. The third aspect associated with the second law is the determination of theoretical limits of a process. Or if you perform any process or a cyclic process, this second law would help you determine the theoretical limit. That means, for example, efficiency is one of the method to determine the effectiveness of your process. So the second law would give you an idea that what is the maximum efficiency, maximum efficiency that you can have for a process, for a cyclic process. Once you know the maximum efficiency that you can have for a process, you would be, this is the basically the ideal case. Ideal case would give you the maximum efficiency. So how far you are from the ideal process is gauged by the theoretical limits. For example, you have heat engines or refrigerators, they are engineering devices. So what is the maximum efficiency of a heat engine? That means if I input certain amount of fuel, what is the maximum amount of kilometers that I can travel with that fuel if my heat engine is designed in a certain way. So the maximum limit, let's say, is 70%. It says for example, for a certain heat engine, the theoretical limit is 70%. That means uh, out of the energy which is being provided to the heat engine in terms of fuel, you can extract 70% of that energy maximum. This is the theoretical limit. You cannot have an engine which has an efficiency more than that of 70%. This is the limit which is uh, uh, defined or calculated using the second law. So if this is the maximum, let's say my system is performing or my system is giving me an actual efficiency of 30%. So I still have room of 40% for the improvement. Do you understand what I'm referring to? Why is the theoretical limit important for us?
Yes, sir.
All right. So these aspects are basically they are dealt with the understanding of second law or the information associated with second law. Now we'll hold on here for a minute and we'll try to move towards the concept of energy reservoirs, thermal energy reservoirs. When I say thermal energy reservoirs, they basically refer to reservoirs in which large amount of energies could be stored without causing a significant change in temperature or without causing a change in temperature. So, uh, thermal energy reservoir is a hypothetical body with relatively large thermal energy capacity. It doesn't say it should have a large mass or a large volume. The large thermal energy capacity. That means one is its mass could be very large, very huge mass. The body could have a very huge mass, or the specific heat, the amount of energy required to change its temperature. This value could be very high. So either of the two, or both of the two. So a hypothetical body with relatively large thermal energy capacity is thermal energy reservoir. This reservoir can supply or absorb limited amounts or finite amounts of heat without undergoing any change in the temperature. Is this definition clear to you what a thermal energy reservoir is?
Yes, sir.
G?
Yes, sir. Clear, sir.
All right, all right. So now let's have an example of it. In practice, large bodies of water such as oceans, lakes, rivers, your atmospheric air, they can be accurately modeled as thermal energy reservoir. Why? Let's say I have a cup of hot coffee at 50 degrees centigrade, very hot cup of coffee. If I drop that cup of coffee into a lake which is at, let's say, 27 degrees centigrade, what would happen to that, the temperature of the lake?
No change. Okay.
It would not change. It would not change. So the finite amount of heat that is being transferred to the lake would not cause any change in temperature of that thermal energy reservoir. So essentially, reservoir is a body whose temperature gets uh, unchanged if certain amount of heat is being supplied by that body or absorbed by that body. And it is not necessary that this body is a very huge body. For example, you take your room. Let's say today the temperature in your room is 20 degrees centigrade, and you have turned on the TV in your room. The heat released by the TV, would it cause any change in the temperature of your room?
No, sir.
No, sir.
No,
All
sir.
right. All right. So with regards to the heat released by the TV in your room is actually acting as a thermal energy reservoir. It gets unaffected by the small amount of heat that is being released by the television in your room, causing any change in your temperature. And if we consider this case, the atmosphere, for example, it does not warm up as a result of heat losses from residential buildings in winter. So, I mean, multiple buildings are using multiple applications. There are heaters that are being used. There are computers and microwaves and fridge refrigerators are being used. So there are multiple applications that are being used in a building that is releasing its heat into the atmosphere. But the temperature, uh, the temperature outside, it doesn't get much affected by the heat losses from the residential building, since the thermal energy capacity of your atmosphere is much higher as compared to the heat that is being lost to the environment or your atmosphere. Clear enough? So your atmosphere is acting as a thermal energy reservoir. Now, uh, do you think a two-phase system can be modeled as a reservoir? A two-phase system.
किस लिहाज से सर?
Let's say you have liquid and vapor in equilibrium together, liquid and vapor. Can you consider that liquid vapor mixture as a thermal energy reservoir?
Yes, sir.
Yes, sir.
Yes. Why? Because this this two-phase system, it can absorb and release large quantities of heat while remaining at constant temperature, unless and until the temperature, the phase change takes place. If you move from two-phase system to a single-phase system, then it cannot be modeled. But as far as the phase system is in equilibrium with two of the phases, the system could absorb heat isothermally. A reservoir that supplies energy. Now we are looking into the categories of the reservoir. A reservoir that supplies energy in form of heat is called a source. Obviously, the thermal energy reservoir. We said that it could supply energy or it could absorb energy. So the one that supplies energy in the form of heat is called the source, and the one that absorbs energy in the form of heat is essentially called the sink. So if you have a thermal energy source and it is providing heat to your system, you could call that thermal energy reservoir as your source. Similarly, if you have a thermal energy reservoir which is basically absorbing heat, you can refer to that reservoir as your sink. Clear enough?
Yes, sir.
Yes, sir. Yes, sir.
All right. Now moving on towards heat engines. In all the three examples that we have seen today, or the two examples that are associated with the shaft work, you had a shaft which was used to generate heat within a system, and then you had electrical wire that was there to generate heat again. This suggests that work can always be converted to heat directly and completely, but the reverse is not true. You have seen work converting into heat in both the cases, but when I asked you heat would convert into work, whether electrical or shaft, you said no, because your experience and your observation suggests so that this is not possible that if you heat up a wire, it would start having electrical energy, or if you provide heat to a shaft, it would start rotating. This is not possible based on your observation. So we had a conclusion that work can always be converted into heat directly and completely, but the reverse is not true. So similar is the case over here. If you have a shaft rotating with a wheel or paddle in water, the rotation of the shaft, which is electrical energy, would convert into internal energy, which would raise the temperature, and that temperature would result in a heat transfer from the system to the surroundings. So this work would essentially result in the generation of heat. But if the same heat is being supplied to the paddle of water, there would not be any work generated, there would not be any shaft that would start rotating. Now, if this is the case, you need to have a device which would convert heat into mechanical energy, and that device is essentially known as heat engine. So you have seen shaft work, electrical work converting into heat directly, but if you want to convert heat into electrical work or shaft work, you would need to have a heat engine in order to do this for you. So now you understand the purpose of a heat engine?
Yes.
All right. Now, can you come up with a very basic example of a heat engine, your everyday use heat engine, where heat is being converted into work?
Sir, engine.
Yes, yes, your car engines. So in a car engine, what is essentially happening is you have a piston cylinder assembly, and there comes in air fuel mixture. This air fuel mixture is being taken up into the system, and the piston goes up, compresses the air fuel mixture. There is an ignition over here, which causes the combustion to take place. As a result of this combustion, the piston moves down and up multiple times. So the air fuel mixture basically provides in the combustion of air fuel mixture basically provides you the heat. That heat is being used to generate mechanical shaft work by this linear motion is converted into the rotational work of the shaft, which is your transmission shaft that starts rotating. So you have an example where heat is converted into mechanical work, and the common example is your car engines or the automobile engines. Uh, so heat engines, they operate on certain characteristics. There are certain characteristics that are associated with the heat engine, and every heat engine that is operating or converting into heat into work would follow these characteristics. There are four characteristics. Number one, they receive heat from high temperature source. They receive heat from high temperature source. In case of automobile engines, the heat is being provided by the combustion of air fuel mixture. This heat could be extracted from solar energy. This heat could be extracted from furnace oil. This heat could be extracted from nuclear reactor. But there needs to be a high temperature reservoir that would give the heat to the engine. Clear enough? Is this point clear? Is it clear?
Yes, sir.
Yes, sir.
Yes, sir.
The second aspect is that the characteristics, which is essential. Heat engines convert part of this heat to work, usually in the form of rotating shaft, but portion of this heat is essentially converted into work, not all of it. The portion which is not converted into heat, it is essentially rejected as waste heat to a low temperature sink. This sink could be atmosphere, it could be rivers, it could be it could be anything. It could be lakes, oceans, uh, just your environment. So there needs to be a low temperature sink for the heat to be rejected to that sink. And the fourth aspect associated with the heat engine is that they operate on a cycle. If you have these four characteristics, you can say that an engine that is working is essentially a heat engine. Clear enough?
Yes,
Yes,
sir.
sir.
Look at the schematic. You have a high temperature source that is giving in heat to the system, Q in. This is giving the heat to the heat engine. Portion of this heat is used or converted into net work out or producing work. The remaining portion of the heat is basically rejected to the low temperature sink. And this process is taking place in a cycle. Now, heat engines and other cyclic devices, they involve a fluid to and from which heat is transferred while undergoing a cycle. This is called the working fluid. So it is possible, or this happens, that heat from the high temperature source is being provided to a fluid which is operating within the heat engine. This fluid takes in the heat, produces some work, releases the heat, and comes back to its original state. So they involve a fluid. Fluid is essential for a heat engine to operate. This is called the working fluid. Now, heat engine is a broader term. The term heat engine is often used in a broader sense. It includes work producing devices that do not operate in a thermodynamic cycle. Rather, they operate on a mechanical cycle, such as internal combustion engines. If you recall the internal combustion engines, you have air fuel mixture that is coming into the system. Air fuel mixture is basically coming into the system. This is basically your fluid. This fluid gets combusted, and there are combustion process and combustion products. Once the combustion has taken place, this air fuel mixture is being thrown out of the system, and there is new air fuel mixture that is being taken into the system. So the fluid that you have, it is not essentially undergoing the cycle. Your fluid is essentially not undergoing the cycle. So is this a heat engine? Yes, this is a heat engine. When a fluid is undergoing the cycle, you would essentially have a thermodynamic cycle. But the cycle in the case of heat engines, is essentially the mechanical cycle where your piston is essentially moving from the top position to the bottom position in a cyclic manner. So it goes up, it comes down. Again, it goes up and comes down. So it is operating in a cycle. Here, the fourth character is not mentioned that the fluid should operate on a cycle, or fluid should move in a cyclic manner. The engines operate on a cyclic manner even if the fluid within the engine is not undergoing a cycle, as in the case of internal combustion engines. You would still have the heat engine. It's a very broad term which incorporates both the fluid undergoing a cycle, or otherwise there is mechanical cycle associated with it. There has to be a cyclic process that has to take place. It is not necessary that it is essentially a thermodynamic cycle. But yes, from the concept of thermodynamics, you are essentially looking for the heat engines which are operating on thermodynamic cycles. We'll look more into it, the power plants which are working on thermodynamic cycles, as we move ahead. But I'll stop over here